Hey guys, in this video we will be doing a video on A-level physics, ideal gas laws, and I found this topic to be particularly interesting. And we will be doing this worksheet I got from savemyexams.com. It's very interesting and I found this a few days ago and it was so helpful for me, so I thought I would share this find with you. So the absolute temperature scale is a theoretical scale proposed by Lord Kelvin, and on this scale 0 is the temperature at which all gases become liquids and ideal gas would exert no pressure. The Celsius temperature is minus 373 degrees Celsius, or water freezes. The first one is indefinitely wrong. The second one is something we can think about. The third one is wrong because 0 Kelvin is equivalent to minus 273 degrees Celsius. And water does not freeze at the absolute temperature, it freezes at 0 degrees Celsius, not 0 Kelvin. So B is correct, but why? Because at 0 Kelvin, we assume that any gas body has a minimum amount of internal energy. We say minimum because it cannot have zero potential energy, because there are molecules and the center of the molecules will have some distance from each other. That is, the nuclei will have some distance from each other, even if the molecules are like totally touching each other. So there will be some amount of electrical potential energy which we cannot take away, no matter how much we decrease the temperature, if we can decrease the temperature. However, the kinetic energy at that point will be zero because we can take all of that away. And without kinetic energy, the molecules will not be moving and they won't therefore be exerting force per unit area and therefore no pressure. And let's see, I think there is actually a pretty great explanation of all of this. It is not possible to have a temperature lower than 0 Kelvin. Sometimes it is suggested that at this temperature, matter has no energy left in it. This is not strictly true. It is more correct to say that for any matter at absolute zero, it is impossible to remove any further energy from it. Hence, absolute zero is a temperature at which all substances have the minimum internal energy. The kinetic energy of the atoms or molecules is zero, and their electrical potential energy is a minimum. Right? And as for the C part, which I told was wrong, let me go into a bit of detail. So we use different symbols to represent temperatures on the Kelvin and the Celsius scale and to convert between them. So if you want to go from Kelvin to degrees Celsius, we have to minus 273 from the temperature in Kelvin. And so if we want to go from 0 Kelvin to degrees Celsius, we have to do 0 minus 273, to which we get minus 273 Kelvin, minus 273 degrees Celsius. Right? Maybe you want to have a bit more knowledge about what the Kelvin scale is and why we prefer it over the Celsius scale, because And the fixed points of the Celsius scale are dependent on a few things like pressure and impurity, and if either of these conditions change, so will the fixed points. But the Kelvin scale isn't dependent on any such material property. It has two fixed points, the absolute zero and the triple point of water, and neither of them are dependent on any physical property of any substance, and that is how they are much more reliable, right? um so that is it, hopefully. So 16, water at 100 degrees Celsius turns into steam at 100. So which of the following statements is true? The internal energy is unchanged, but the kinetic energy increases. The internal energy is unchanged, but the potential energy increases. Both the internal energy and the kinetic energy increase. Both the internal energy and the potential energy increase. And D is right, because internal energy is dependent on both potential and kinetic, and during state of change of state, because the temperature is a constant, that means that temperature is also a constant, and so there must not be any increase in the speed and the kinetic energy, right? We even have this mathematical formula relating the two, which is 3 by 2 kT, where K is thermodynamic temperature, and this is equivalent to 1 by 2 mv square. So because the internal energy is definitely increasing, that means only the potential energy of the molecule will increase, because the distance between the molecule will now have increased, and distance is inversely proportional to the value of electrical potential energy of molecules. Let's just have a go over what internal energy is. The internal energy of a system is the sum of the random distribution of kinetic and potential energies of its atoms or its molecules. And the molecules have different amounts of kinetic and potential energy at different physical states of matter. And then we also have this equation, delta U is equal to Q plus W, where delta U is internal energy and Q is heat, whereas W is work done. So if heat is given such that water becomes steam, there's definitely an increase in internal energy, and if there isn't any increase in kinetic energy, all of that increase in internal energy corresponds to an increase in potential energy, right? So a sample of an ideal gas at 27 degrees Celsius is placed in a sealed container, that is a closed system, and the gas is heated at a constant volume to a temperature of 324. So the volume is maintained and the temperature is increased. So they're asking the ratio of the final pressure to the initial pressure exerted by the gas is approximately what? So this is a bit of a confusing question. No worries. So volume is a constant, but we are increasing temperature, and so pressure is subsequently increasing, right? And this has to do with Charles' law, in which we increase temperature and we keep the rest of it a constant. So we have actually learned quite a few different kinds of equations previously, and they did incorporate a lot of that pressure, volume and temperature stuff, and one of these was PV is equal to nRT, and this is called the ideal gas equation, right? So in this ideal gas equation, because we are keeping the volume constant, we don't need to really consider this at the moment. R is a constant and therefore always a constant, and N is a constant because it is a sealed container, so we aren't letting any of the molecules increase. So when temperature increases, so does the volume. These two are directly proportional, so to speak. But you need to remember that the temperature we are talking about this is thermodynamic temperature. So when we take the ratio of initial and final temperature, we must first convert them into the thermodynamic scale and then take that. So to go from degree Celsius to Kelvin, we need to add 273. So we have 300 Kelvin. And what about here? 324 plus 273, 597 Kelvin. And so by how much has the temperature increased? We divide 597 divided by 300, so it should be about 2 times. So it's 1.99. So if the temperature has increased by this amount, then so will the pressure. So the ratio of the final pressure to the initial pressure will be 2/1, because 1.99 is basically 2/1. And these two things, this pressure and this temperature when volume is constant, are directly related. So this is the answer. So now they'll be asking difficult questions again. The average kinetic energy of the molecules in an ideal gas is directly proportional to the square root of the absolute temperature, directly proportional to the absolute temperature, independent of the absolute temperature, inversely proportional to the absolute temperature. And so the relevant equation is this one. EK is equal to, this K over here is kinetic energy, 3/2 into K into T. This K over here is another constant, and so we don't need to take that into account. So when we increase this by a certain factor, EK also increases by the same factor, because these two are directly proportional. So which one is right? This one. However, if they had asked the relationship between speed and temperature, it would have been different, because EK is equal to 1/2 into m into v square, speed squared. So the relationship would have been different between temperature and speed. So we have two different sized boxes, P and Q, and that means that the volume is different. They both contain the same number of nitrogen molecules, meaning N is the same. And the molecules in box P have twice the root mean square speed of those in box Q. So which of the following must be correct? So we have different volumes but same N, and the molecules in box P have twice the root mean square speed. So the density of the gas in box P is greater than that in box Q. Is that true or is that not true? So there is this equation which we studied. Where the hell does this go? In which PV is equated to 1/3 into capital N, and here is the number of molecules. 1/3 into n into m into the square of root mean square. So what they are saying is that n is the same because the number of molecules is the same, mass is the same, because we're talking about both of them being nitrogen molecules, right? So what is n into m? This would be m. So if we change this equation up, right, so we took v over here, we will have m over v, and this is actually the density. We keep pressure over here, we multiply it by 3, and we divide all of this by the square of root mean square value. But the problem here is we don't know what the volume is. And though we do know that m is the same, nor are we all that sure about what the pressure is. Because there's also this PV is equal to nRT is equal to something or other. And when we compare temperature with 1/2 mv square. So if P has twice the speed, right? So if this particular box P has twice the speed, then that means that its temperature is 4 times, right? So it's 40 for that one. R is the same and N is the same, right? These two things are the same. So now we're talking about P into V. So the volume is different, and the pressure may also similarly be different, and this is a bit sure about that. And they're saying that the mean momentum of the molecules in box P is greater than that in box Q, and the mean momentum is m into v, right? Well, the mass is the same, but how can we show about the mean momentum being the same? Because the molecules in box P indeed have a greater momentum, but there isn't anything of a surety, because when we take the mean momentum, we take the mass and multiply it by the average speed and not the root mean square speed. Those two things are different. They are entirely different. in this scenario the mean speed of p might actually be 0, because all of the particles are going equally in all the three different directions. Hopefully this makes sense. And if it doesn't, I'll just simply read out a passage from this book. About the importance of root mean square and why do we have that thing even. So we'll just go over how this whole formula comes about, and on the way the significance of root mean square speed will become clear. We can use the kinetic model to deduce an equation which relates the macroscopic properties of a gas, which are pressure and volume, to the microscopic properties, that is mass and speed. We start by picturing a single molecule in a cube-shaped box of side L, right? So we assume we have this cube. Oh my god, terrible. Oh my god. Let's just think it's some sort of a cube, right? It really distorted, and there's this molecule right over there. And let's assume that this is L and this is L2. And this molecule has mass m, alright? We assume that this single molecule has a mass equivalent to m. And it is moving with a speed which we term as c, parallel to one side of the box, right? So it's moving like this, or maybe it's moving like this. So basically, whatever direction it is moving, it has to be parallel to either one of the sides of the box. And so it rattles back and forth. It hits one extreme, goes back, hits the other, and returns. So this is its sort of motion. And so it collides at regular intervals with the ends of the box, and therefore contributes to the pressure of the gas. And there are regular intervals because we assume for an ideal gas that the kinetic energy is conserved. There is no change in the kinetic energy of a molecule because all collisions happen to be termed as elastic. And what we want to do is that in this particular scenario, we want to work out the pressure exerted on one end of the box and then deduce the total pressure produced by all the molecules. So by deducing an expression for the molecule's pressure exerted on one side of the box, and from that we will get a expression for the total pressure produced by all of the molecules in this particular cube-like container. So if we consider an equation and molecule which is hitting this side of the cube, so it rebounds elastically in the opposite direction, meaning it goes over here, hits over there, and then rebounds elastically in the opposite direction. So initially, if it had a speed of c, because this is velocity and then after the rebound it will have a velocity equivalent to minus c. And therefore its momentum will change by an amount to mc, because initially it had a momentum of m into c. Now it has a momentum of m into minus c, and if we take the difference we get 2mc. So we now have a value of the momentum change as a result of a single elastic collision of one molecule traveling parallel to a side of the cube container, right? And so between consecutive collisions with side A, B, C, D, as in it goes from here over there, hits it again, and then returns, right? So it basically hits and then goes back and comes again. So between two consecutive collisions, it travels a distance equivalent to twice the side it travels parallel to, right? And so if v is equal to s over t, so t is equal to s over v, that is distance divided by velocity. And if distance is 2l and speed is c, it is 2l over c is the time interval between consecutive collisions. And now we have value of time and value of momentum change. So what is force? We learned about this in AS. Force is defined as a rate of change of momentum. So we basically divide 2mc by 2l over c. So this goes over here and we get mc square over L as the pressure. And now we want it as a force, and because we want to know the pressure of one molecule, pressure exerted by one molecule on one side right, it will take into account the force exerted and how much times the force is exerted. And so we divide mc square over L by L square, because this is a cube and the length and the width are equivalent. And when we get this expression, which is mc square over L cube, and that is the pressure exerted on one side, that is ABCD, by one molecule present in a cube-like container. And we have made a lot of assumptions, one assumption being that this molecule is traveling in only one of three possible directions, in the x, the y, and the z. And so we are assuming this particular that it is only traveling in the y direction, and so it always hits this side, right? So there are a lot of assumptions. And moreover, this is just one molecule, but there is a large number n of molecules, and the number is represented by capital N. This represents the total number of molecules, and each of them will have a slightly different velocity between extremes, and each of them is individually contributing to the pressure. So to find the total pressure, what do? We multiply all of this by n, and instead of taking c, which is the speed of one particular molecule, we take CRMS, which is sort of like an average, but not really an average of all the different speeds all of the molecules can have. It is not the average, actually. It is something different, because if we take the average, chances are that it will equalize to 0. That is not what we want. But even though we still have this, and now we've taken into account that we have more than just one molecule, and we've taken into account that all of these molecules will have slightly different speeds within certain extremes, but still this equation isn't quite complete. And why is that? Because we are still assuming that all the molecules, that all of these n molecules, they're all traveling in the same direction and are colliding with the same space. So we're assuming that all n are like doing this, but that isn't what is happening, because all of them are moving in 3 dimensions equally, which is why we don't take the average, because if we take the average of the velocities, we will get a value of 0. So we need to divide this by 3 to get the actual value of the pressure. And voila, this is the complete pressure equation. Again, I am hoping you got the importance of RMS values. And because L cube is equivalent to V, we can substitute for that. And we can actually bring V over here. So we get PV is equal to NMC RMS square divided by 3. And so we can also equate this part with with nRT. And this n is small n because this is the number of moles and not the number of molecules, because this is also equivalent to PV. So we can sort of like correspond these two equations to get another one. And capital N into M is actually the mass of all the molecules of the gas, and this is simply equal to the mass M of the gas, capital M. So Nm over V is fundamentally just the density of the gas. So we may say that the pressure of a gas is dependent solely on its density and the mean square speed of its molecules. And let's move on to some other aspect of this chapter. So the pressure exerted by an ideal gas maintained at a constant pressure is inversely proportional to the volume, right? So which of the following statements is not correct? The average molecular kinetic energy remains constant. Yes, it should. The gas must consist of identical molecules. That is a bit weird. The mass of the gas is fixed. Well, duh. And the number of molecules in the gas does not change. Yep, it does not. Yes, we're using the equation PV is equal to nRT, and according to that, for pressure and volume to be inversely related, the number of moles of the molecules should be the same, R is always the same, so T. So I guess the answer will be B, because the gas must be made up of identical molecules, because we are using N over here, that is the number of moles of the gas, of a particular gas, whose pressure and volume are inversely proportional. So in the equation 1 by 2 mc square is equal to 3 by 2 kt, the term c square represents the mean speed of the molecules, the mean speed molecule squared, the mean square speed of the molecule, or the mean velocity of the molecules. What term do we use for this? So we shall call this the mean square speed of the molecules. So the molecules in the material may possess kinetic and potential, and the internal energy is equal to the sum of both of these. It is defined as the sum of the random distribution of the kinetic and potential energies of the atoms or molecules that make up a gas body or whatever else. The average kinetic energy of the molecules in a gas is proportional to the total mass of the gas, the temperature of the gas, definitely, the specific heat capacity of the gas, nah, the number of molecules in the gas, nah. So the answer is C. So they're saying the relative masses of oxygen and hydrogen are 32 and 2 respectively, and for any temperature the ratio of the root mean square speed of oxygen over hydrogen is given by you should know that for any given temperature the mean average velocity of all the molecules is the same, and if oxygen is 16 times heavier, right? If this is 1 by 2 into 16m into x is equal to 1 by 2 into m over y. So we are taking x over y. This will just be 1, 0.5 into m over 0.5 into 16m, 1 over 16. But the thing is, all of these are actually squares, so we have to take the under root, and so the under root is 1 over 4. So the answer is B. Because mass is inversely proportional to the square of the velocity. Samples of nitrogen gas and helium gas are at the same temperature, right? So this is the same thing again. A sealed gas contains a mixture of different gases. At a given temperature, the mean kinetic energy of each molecule depends upon how much of each gas is present. It doesn't. Yep, it's greater for the gas with the less massive molecules. And why is that? Because 1 by 2 into m into v square, right? So we have a mixture of different gases and they're all at a given temperature. And the mean kinetic energy, what will it be dependent on? We know that 1 by 2 into m into v square is equal to 3 by 2 into k into t. And so if temperature is a constant, it means 1 by 2 into m into v square is a constant for all of them, right? So m into v square is inversely proportional, right? Right? So if something has a larger mass, this is actually a bit confusing. There are some other equations as well. So if the temperature is the same, it means the kinetic energy ought to be the same. Yep, is the same for each gas in the mixture. Because at the same temperature, stuff will have the same amount